What if the ghost of the universe is a neutrino no one can touch? Meet the sterile neutrino, a particle that feels only gravity. It does not use the weak electromagnetic or strong forces, but it can mix with normal neutrinos. Why care? Because this could be dark matter, shaping galaxies, easing neutrino masses, and even seeding cosmic history. In 5 minutes, what sterile neutrinos are, how they could be dark matter, and how experiments are testing them. Standard model neutrinos, electron, muon, tau, are ultralight and use the weak force. Sterile neutrinos are invisible to those forces. Through mixing, active states can oscillate into sterile ones. In seesaw models and the NMSM, adding sterile states helps explain why active neutrino masses are so small. These models can also help with the universe's matter-antimatter imbalance and give a dark matter candidate. To be dark matter, a sterile neutrino must be heavy enough, long-lived, and produced in the right amount. Often keV mass if it is warm dark matter. Mixing must be tiny so it barely decays or scatters. Its birth in the early universe must match CMB and structure data, not too fast, not too warm. Non-resonant production, Dodalson-Wydrow, oscillations in the hot plasma make a warm spectrum. Resonant, Shy-Fuller, with lepton asymmetry, mixing is enhanced and the momentum distribution becomes colder. Other ideas, freeze-in or decays of heavier particles, sometimes in a hidden sector, to tune abundance and speed. Colder spectra preserve small structures, warmer ones erase them. Bottom line so far, keV masses with very small mixing are still possible. But the window is tight. Now how do we test the invisible? Enter neutrino observatories, labs, and the cosmos itself. IceCube uses atmospheric muon neutrinos crossing Earth to hunt for sterile mixing. In a 3+1 model, some NEM could oscillate to sterile states, making direction and energy-dependent deficits. High energy, 320 GeV-20 TeV data, about 100,000 events in 1 year, showed no anomaly. It excludes parts of DM2, 0.110 EV2, with mixing around SIN2, 242, 0.02, near DM2 3 EV2. Deep core pushes to 10 the 100 GeV, and sets world-leading limits on some elements like UT4. These are strong EV scale tests, but they do not reach the tiny keV scale mixings for dark matter. Dune will fire a well-known beam to a huge FAR detector to test sterile hints with precision. Sterile states do not do neutral current interactions. A deficit at the far site would be a clear sign. Dune is set to sharpen constraints on mixing with tau flavor, especially at 34. It may also chase heavier neutral leptons via visible decays or magnetic transitions, if lifetimes allow. Results await operation. Sensitivity depends on exposure, resolution, and systematics. Katrin reads tritium V decay near the endpoint to spot a kink from a heavier sterile state. Early runs probed up to about 1.6 keV masses, but mixings relevant for dark matter are far smaller. Future stats and backgrounds may improve limits, yet astrocosmo bounds dominate at tiny mixings. If sterile neutrinos radiatively decay, they make a monochromatic X-ray line at energy. 1 Noir 2 Miss New Star and others set strong limits across 3 to 20 keV, cutting deep into the allowed space. To avoid detection, mixing must be extremely small. Only small regions remain if it is all the dark matter. Lyman, satellite counts, and lensing test how warm dark matter is by its small-scale smoothing. Many models need mass of at least a few keV, often HAWK 10 keV or higher, unless production makes it colder. CMB observables limit extra radiation and neutrino sums, keeping mixings very small. Hidden sector stories can cool or suppress production, but add model complexity. Summary so far, big swaths excluded. keV masses with ultra-tiny mixing and colder production remain viable. Open windows, masses of a few tens of keV with very small mixing depending on how they were made. Typical dark matter mixes, about 10.6 to 10.10 or smaller, beyond most lab reach today. Resonant production or hidden sector freeze-in can make the spectrum colder and keep structure intact. Heavier sterile neutrinos, MEV-GeV, may exist too, though not as all of dark matter. IceCube and Deep Core now disfavor many EV-scale sterile solutions, once hinted by anomalies. June will probe neutral current deficits and T-sterile mixing, pushing the frontier. Indirect dark matter searches in neutrinos can also be reread with sterile mixing in mind. Next-gen X-ray telescopes will deepen line searches and narrow the mixing window. Better Limina and small-scale galaxy data will sharpen warm dark matter bounds. V-decay experiments could reach new sensitivity with huge statistics and strict backgrounds. Theory is active. New interactions, altered thermal histories, and dark sectors are all on the table. Bottom line, a sterile neutrino can be dark matter, but only with key EV masses, ultra-tiny mixing, and the right production. Large regions are ruled out by X-rays, structure, and oscillation data. A small island remains. The next decade, Dune, sharper X-rays, richer cosmology, could decide the story. If the universe hides its matter in sterile neutrinos, we are closer than ever to finding the whisper. For daily cosmic adventures, subscribe to Universal Universe, then share and like to keep this journey alive.